Hi everyone, we are Group FT26 and our topic is sentiment analysis using Naive Bayes. Our problem statement focuses on how restaurants receive many customer reviews daily, making it hard to manually go through all of them and extract useful insights for improvement. Our objectives for this project is to classify reviews into positive, negative, or neutral, to compare classifiers and evaluate the performance based on accuracy and matrix. So what is sentiment analysis? It's a natural language processing technique that helps identify if a text expresses a positive, negative, or neutral feeling. In our project, we applied sentiment analysis to Google food reviews, which helps restaurants quickly understand customer satisfaction and areas of improvement. We used the Kaggle Malaysia restaurant review dataset, which contains over 526,000 reviews collected from both Google and TripAdvisor. The sentiment class are positive, neutral, and negative, and it is balanced. We chose this dataset because it is closely related to our Singaporean context, as it has local style language and Singlish expressions such as shiok, which makes the dataset more relevant and realistic for our country. This helps our classifiers understand and classify sentiments more accurately based on how people here actually give their reviews.
So for the classifiers we use for training are naive Bayes, logistic regression, and SVM linear SVC. Next slide, please. Naive Bayes is a probability-based classifier. It uses Bayes' theorem to estimate the likelihood of each sentiment class based on the words in a review. It assumes each feature or word contributes independently to the final prediction. By using this formula, the model calculates which class has the highest probability and assigns that sentiment to that text. Next slide, please. There are different types of naive Bayes, but for this project, we specifically use multinomial naive Bayes. This version is designed for text classification because it works with word frequency, which is exactly what we have in our TF-IDF reviews.
So our second classifier is multinomial logistic regression for our three sentimental classes. It is a discriminative model that uses softmax to output the class possibility. So during the training, it learned the relationship between TF-IDF features and sentiment by maximizing the log likelihood to predict with actual label. It suits text because of the TF-IDF data being high-dimensional yet linearly separatable enough. The softmax layer provides a probabilistic prediction for confidence comparison. L2 regularization prevents overfitting in data with thousands of features. However, it struggles with non-linear sentimental cues such as sarcasm and slang, and is vulnerable for class imbalance. So our third classifier, linear SVM, is discriminative and it finds the optimal hyperplane with the largest margin to separate the sentimental class. Unlike logistic, it predicts the probability. For the class analysis, we use one versus rest strategy to train a model for each class, and it helped to minimize the classification error while maximizing the margin between the decision boundary and support vector, which typically enhance the generalization. It excels at sentimental classification on high-dimensional text like TF-IDS, easily finding a separating margin. However, its limitations include struggling with overlapping or noisy sentimental boundary, which often require tuning of regularization of parameter C or suitable kernel. Despite this challenger, SVM remains to be a strong, reliable baseline due to its margin-based approach and excellent handling of high-dimensional data.
Next, we move to the reprocessing and classifier implementation steps. So, to prepare our data, we first clean the text by converting it to lowercase and removing stop words and emojis. Then we tokenize each review into individual words. We split the data into 80 and 20 for training and testing to ensure unbiased evaluation. Finally, we apply TF-IDF to transform text into numerical vectors for our models. So basically, a word will get a high TF-IDF when it appears frequently in a document and it appears rarely in all other documents. Common words like good or food will get lower weights than the distinctive words like overpriced or excellent. Next.
Before pre-processing, we derive three word cloud. All three word clouds looks very similar. Common domain words like food, good, place, price dominates every class. These words do not show real emotion and do not help the model separate positive, neutral, and negative. So the word cloud is noisy. Next. After pre-processing, where we removed words such as restaurant, place, food, etc., now the word cloud shows more meaningful sentiment words. Example, delicious, bad, okay. This shows that pre-processing successfully removed noise and allowed true sentiment patterns to appear clearly. Next. To properly experiment with semantic content, we trained our classifier using both unigram and bigram. This is critical because sentiment often changes when words appear together. For example, good by itself is positive, but not good expresses a negative meaning. Okay, next. For result and discussion, for naive Bayes, we can see that all three classes perform well, with strong precision and recall across negative, neutral, and positive. Overall accuracy is 86.9%, which indicates NB was able to classify most reviews correctly. Neutral is slightly weaker than the other two classes, showing that it still struggles a bit with mid-tone or borderline reviews. This behavior is expected because naive Bayes is vocabulary frequency driven. It calculates sentiment based on how often words appear in each class. Positive words like good appear widely across review, so naive Bayes may still slightly lean towards positive prediction sometimes. Next. Looking at the confusion matrix for naive Bayes, we can see that while the model performs well overall, it still shows a slight bias towards predicting the positive class. NB correctly identifies a large number of positive, neutral, and negative instances, but we can also see that neutral and negative reviews are sometimes misclassified as positive. This indicates that naive Bayes still struggles with the subtle sentiment boundary between neutral and positive. Overall, this matrix confirms that NB performs strongly but still tends to lean slightly towards positive when uncertainty happens. Thanks.
For the logistic regression, it achieved the balanced performance across the three sentiment classes with around 89% accuracy and a macro F1 of 0.8. It performs better than naive Bayes, especially in detecting neutral and negative reviews, because LR learns which decision boundaries in the TF-IDF space, adjusting the importance of each word to reduce bias toward positive reviews and produce more stable, well-balanced sentiment classification. Looking at the confusion matrix for error, we can see improved class separation compared to naive Bayes. The number of neutral and negative reviews misclassified as positive is much lower because error can learn discriminative weights, allow it to better distinguish mid-range reviews and minimize the overlap between the neutral and the positive classes.
For SVM using linear SVC, we can see that all three classes perform very well with high precision and recall across all three classes. The overall accuracy stands at 92.2%, making it the strongest and most balanced classifier among the three. Unlike the other two classifiers, SVM demonstrates excellent stability across all sentiment classes, showing no significant bias towards any specific label. This balanced behavior is likely due to SVM's ability to form clear decision boundaries in a high-dimensional TF-IDF space, effectively separating the different classes. Overall, SVM shows reliable performance in handling subtle differences in tone across the reviews. Looking at the confusion matrix for SVM, we can see that it correctly predicts a large majority of all three classes. Misclassifications are minimal with only small overlaps between classes, such as negative being misclassified as positive 644 times. This shows that SVM effectively captures subtle linguistic variations and maintains a clear separation between all three classes. Compared to the other two, SVM performs with higher precision and better overall class balance, confirming it as the most robust classifier in our sentiment analysis project.
Here we compare the top 10 positive words from each model. Naive Bayes focuses on frequent and domain-specific phrases like lovely ambience. Logistic regression highlights universal words like excellent and love. And SVM emphasizes words that best separate classes, handling subtle tone differences better. So while they share similar words, each model interprets them differently. The table shows unigram versus bigram results. Adding bigram improves performance, especially for SVM, and especially for SVM and logistic regression. The models capture short phrases like not good or very slow, which holds stronger sentiment than single words. Hence, we use bigram for better context and more accurate predictions. We chose SVM as the final model, and it delivers the most balanced and consistent results across all sentiment classes. By maximizing class margins, SVM handles overlap and subtle tone shifts effectively. It's less biased by frequent words and generalizes the best overall, making it our most reliable sentiment classifiers. So next, for our demo, So here you can see we did a website using our SVM model to train a sentiment analysis web app. So we scraped hundreds of Google Maps reviews from Singapore restaurants and cleaned them into a CSV dataset. So for example, you type ramen and you choose this one. You can see that the overall sentiment is 79% positive, 11% negative, and 8% neutral. There are top phrases and top issues that you can see here, and the total reviews as well. And here is from a business owner's perspective, these insights highlight what to amplify and what to fix, helping restaurants improve service, streamline operations, and monitor customer satisfaction over time. And it turns raw customer feedback into clear, actionable insights powered by a SVM model. Okay.
When we first trained our models using only the Google review dataset, we realized that the data was highly imbalanced. Most of the reviews were positive, which caused the classifiers to become biased and led to inconclusive comparisons. For example, Naive Bayes achieved the highest positive F1 score, but completely failed to identify neutral values accurately. Logistic regression SVM performed more evenly overall, but they also struggled with the neutral class. Because of the dataset imbalance, these results weren't fully reliable, and it was difficult to determine a clear best classifier. To address this issue, we later combined the Google and TripAdvisor datasets, creating a more balanced dataset. All the final evaluations and performance results shown earlier were based on this improved balanced dataset, which provided a much more fairer and more accurate classifier comparison.
So our approach has several limitations we can address. And starting with pre-processing, our stop word removal accidentally filtered out sentiment critical words like not, but integrating a sentiment lexicon which solved this. Moving to feature extraction, TF-IDF only captures word frequency without understanding context. So switching to contextual embeddings like BERT or word2vec will give us much richer sentiment meaning. On the modeling side, our linear models struggle with complex nonlinear patterns. So we would like to optimize our hyperparameters running grid search CV, which would likely give us a significant performance boost across all models. So looking at our results, SVM performed best with 0.922 accuracy on the balanced dataset, beating logistic regression at 0.899 and naive Bayes at 0.869. So naive Bayes particularly struggled with the neutral class. Okay, and the key finding was that our initial unbalanced data set hurt all models, so they failed to predict the neutral sentiments properly, showing how critical data set quality is. So moving forward, we should use contextual embeddings like BERT instead of TF-IDF and apply hyperparameter tuning through grid search CV. And that is our conclusion. Thank you.